Mhm.
All right. Okay, the recording is started. So, yeah, this work is uh, we've been working on it for the last year or two. The excited state densities from the linear response density TDDFT. And well, the motivation behind it is, well, first of all, our interest to figure out, can we get the excited state densities from the linear response? It's not quite clear because basically the excitation properties that we get such as from TDDFT, such as excitation frequencies, oscillator strengths, transition densities, we get them using the time-dependent perturbation theory, and that does not come, and the excited state densities do not come up naturally from time-dependent perturbation theory, and therefore we need to find a way to do that. Okay, we can actually get that from first order time independent perturbation theory by taking a functional derivative of the total excited state um, energy. So if we have all the ingredients, the ground state energy and the excitation frequency, we get the excited state density as well, the sum of ground state density plus the following derivative and
Mhm.
in red.
Mhm. Mhm.
This approach has been previously explored by chemists for adiabatic excited state density in the Kohn-Sham orbital basis. Uh, what we are going to do is we'll get the non-adiabatic formulation for them directly in real space. And of course, we will use the linear response DFT because linear response DFT gives the excitation frequencies from as the eigenvalues of this equation, where the, well, I guess you pretty much
Yeah, yeah.
familiar with this one.
Sure.
Yes. So, right. So what we do with this is we take the derivative of the whole equation, and I
No, no,
think,
no. I'm still trying to formulate what I want to ask,
all right.
but keep going in the
Yes.
meantime.
So the
Because no, sorry, I think now I know. I mean,
mm,
so the first equation that is delta. So Ni is the excited state
yes, this is the excited state density.
density. I mean, this is not, I mean, the response equation would be like a density is integral over response function times perturbation, right? And then, so this is not, so where this comes from, this is not that.
It's not that.
Yeah. I think maybe I would like to,
This is something that
I would like
Is
to
it
sort of, I
here?
mean, there was this equation right here. I mean,
Mm, well,
I can sort of, you know, see what that equation is, but I would like to sort of maybe
right.
sort of
So
go
can I
back.
jump in? Yeah, because
yes, please.
so when we
Yeah,
when originally when I was it was only very recently, right, that I realized that that TDDFT gives access to excited state densities, right? So from time dependent perturbation theory, you get transition densities, and and like that density that you just said, the chi and squared, you know, you get a transition density, right? And that's based on time dependent perturbation theory. And then you know, there's all this work in this literature from Philip Fourchet and so on, where they say, oh, you can get excited state densities through this variational method. But how can you? Because and so, but then the thing is, it's time independent perturbation theory. So if you know, like if you think about like just the first order in normal quantum mechanics, one body even, the first order change in the energy when when a potential due to a different potential is the expectation value of that perturbation in the state of interest, right? So let's say psi I, right? You take then V, you know, your V expectation value of psi I, but that V is a a local
Oh
position.
yeah, okay,
Yeah, yeah,
right.
yeah.
So you simply, okay.
And
So it's this matrix element, the functional derivative.
exactly.
Whatever is left is, of course, the Ni.
Yeah, so it's just then Ni. Yeah, in other words, E.
I see. So, yeah, right. So, okay. So, oh, I see. So, okay. So the change in energy responding to a perturbation, yes, is of course this matrix elements, and then you take the derivative, and then yeah. Okay, so now I get it where that comes from.
And it's interesting because
Yeah.
when we think more
Yeah.
in the time-dependent case,
Yeah,
you
we don't think that way.
Yeah, and I for the longest time thought that Philip's thing was an approximation, but no, in principle, I mean, he does an
Well, I mean,
approximation.
you can just write it down using the exact many-body wave function, right? I mean,
Yeah, you could, but then to access it from the TDDF, from
that's of course, yeah.
This is interesting because you do get it from the excitation energies, right?
Okay, sorry. Then maybe go back where we are. So then you take.
So that take the derivative and well define the delta n as the density difference as follows. And well, the derivative of the Cassidy equation, is like this, with n being the normalization.
Oh, okay. So that's, oh yeah, of course.
Constant.
Right.
Yeah,
So you
there is.
get, okay, so you get that.
The derivative of the omega matrix has actually two contributions. The first one here comes from the variation of the Conchamp variables under the V external, like the Conchamp frequencies and FHXC. And the second one is the variation of the solution point omega I itself, which is given by the, which is contained in the FHXC. And for an arbitrary normalization, we would have to deal with this last term. But surprisingly, if we choose the normalization that corrects the oscillator strings, we are able to remove this last term from the equation, which, well, doesn't change the density difference at all. It is not supposed to depend on the normalization choice at all. But we get the more nicely written equation, I would say.
Looks nice. So the G's are the eigenvectors.
Yeah.
And I see. Okay. Yeah, makes sense. I can sort of see that. So, but you need the. Okay, you need the omega matrix. You need
we would need to evaluate all the elements of this new omega matrix derivative. And
then yeah, okay.
Yeah,
and then you need to contract that with the eigenvectors. Okay.
Yeah. So, well, I did not provide the full equation for each, well, for the general omega matrix derivative element, but what we started doing at first is, well, an approximation. The small matrix approximation, when we consider that the true excitation can be described by the dominant Conchamp transition, and the omega matrix naturally reduces to just one diagonal element corresponding to it. And correspondingly, the delta n, the density difference, reduces to the one single element of the omega matrix derivative. Again, with the same normalization that we introduced previously. So yes, and what we have to do here is to evaluate the parts of this derivative, namely the derivative of Conchamp frequency and the derivative of the FHXC kernel. If the first one does not pose any problem, the second one, well, there is a question we have to address. What do we do with the frequency dependence in here? Because, well, of course, if we can do the adiabatic approximation and remove the frequency dependence at all, and that would work for some systems, but we would definitely lose the double excitations. And, well, if I gave this talk yesterday, I would refer to the next talk of the year when we were very interested in the dynamics of double excitations, and where we needed these double excitation densities to run the RRTDDFT. Well, here, right, we are losing them. Well, the one, I'm not sure if that's informative, but we can try the frequency dependent kernel from Bethe-Salpeter equation, but that's actually not quite.
That's a pain.
Yeah.
We don't want to do that.
Yeah, we don't want to do that.
No.
Not practical for large systems. Then another approach that we might use is the address TDDFT, which gives a few matrix elements of frequency-dependent FHFC. But if we look closely at the derivative itself, it contains infinite sum over a large span of matrix elements of FHXC. It's well, the elements available from address TDDFT is not enough. Like, and at least because the FHXC in the equation for the densities isn't, well, that's not even limited by the transitions, quantum transitions from occupied to unoccupied states, because you can see P here, the index P, it runs for all the occupied and virtual states. So what we decided to do instead is not to use the general formulation for SMA densities, but derive delta n by taking the derivative, well, not of the exact excitation frequency that we can define from linear response, but from an available non-adiabatic approximation. And that one is available from our colleagues' previous works on the addressed single matrix approximation. Right. I'm not, you know, right? So it's the frequency dependent kernel given by the diagonalization of Hamiltonian in truncated three states with single excitation Q and double excitation D. So this equation gives two solutions, and well, not quite surprisingly, when we take the derivative of this equation, we get two distinct density differences for the two states. So this new equation contains explicitly the density of the single excitation Q, which we called delta n ASMA, because it can be approximated by SMA.
Adiabatic small matrix approximation.
Yes, and the second is the double excitation character density, which is the delta of HD minus H00 over. And there is also the coupling term, but in most of our examples, the coupling term does not bring a huge contribution to the densities.
Relatively small.
Yeah.
And
And
I have a quick question.
right?
I can't remember now. So this G plus minus, is this peculiar to the?
That's for this
particular
yes, for
area?
this particular frequency dependent kernel. I think it's also
DSMA 0 or the DSMA.
Yeah, I'm not sure about DSMA 0.
Okay.
Yeah, this this non-adiabatic kernel is what DA in his talk called DSMA Anya.
Yeah.
Because it's a little bit different from what Dawood and Nipa has introduced in their paper, because of this omega SMA that I only put to derive more derive the equation for the density like this with the
I mean, the structure is very similar, but there's some choices. For example, if you just diagonalized in the 2 by 2, instead of where you see the omega ASMA, instead of that, you'd have like HQQ minus H, like the single excitation, things like that. So then for various reasons, we, made these variants where you replace things with TDDFT type stuff. And this is one of the variants that Anya came up with.
Yeah, I also didn't put much of attention before to the G squared coefficient. Well, in SMA, we generally have it from the eigen from the eigenvector, and you can see that in the DSMA density difference, we also have the coefficients related to the g squared of the state we are looking at. So this g squared is multiplying the adiabatic single excitation part, and 1 minus g squared, which is actually, which would be g minus plus in this case. So the wait, how not to get too confused myself. Yeah, the g squared plus and g squared minus should add up to 1, because
Well, because within this thing, that cone-sham oscillator strength that gets distributed wholly into these two things.
yeah. Well, so
Yeah.
we came up to the conclusion that g squared actually is quite important in the description of the double excitation properties, including the density differences.
Anya is 11, and we started late, but just so we don't.
All right.
Okay.
So
Like wrap up
fine.
in 5 minutes.
Okay.
maybe. Yeah.
Finally,
So-
the results for So we checked the one-dimensional two-electron systems in the harmonic potential with a slope tuned by the parameter gamma. Gamma also tunes the degree of mixing of the single and double cone-sham characters in the true excitations. So at gamma equal to 0, this mixing would be the largest, and at gamma equal to 1 on the next panel, that that separates the two true excitations quite well.
You want to separate the single and double.
Yes,
Otherwise-
exactly. So in the single and double in this case would be the second and third excitations correspondingly. The first one has no double character in it, so it is quite well approximated by adiabatic SMA in red. And in this case, we calculated both densities with the frequency-dependent kernel. Well, wait, with FHXC kernel, with the adiabatic part being an exact exchange.
Yeah.
Right. So, right, the exact exchange gives perfect adiabatic density differences for the first excitation. However, at the case gamma equal to 0, it fails to describe both excitations at all, because those are.
I see. So this comes out. So just remind just remind me, if I were to take just the cone-sham densities without doing any TDDFT, what would that look like? So how large is the correction that gives you this nice agreement?
In this case, I did not include the cone-sham.
But probably the single excitation would probably be very similar to A. Right.
Yeah, it's probably
similar. Yeah.
Presumably, it's probably not a large
difference. For the double, I'm not
correction,
sure
but
how
the
much.
double is probably more dramatic. So the double, let's see,
Well, we just resubmitted it. So
so the double, which is so let's see here. The exact looks like, so that's the second one, no? That's the second and third. I see.
Yeah. Second.
Okay, so the second and third, they have this double excitation character. Which one has the double excitation character?
So in gamma equal to 1, they both have about 0.5 share of the double cone-sham double excitation.
Okay.
I think in gamma equal to 1, and it's kind of evident that most of the double excitation is in the third
in the third one.
excitation, because, well, the second is quite well approximated
Yeah.
by adiabatic SMA.
Yeah, so let's take a look here. So that in the inset, that's the density, and the
Yes,
the other curve is the density difference. or what?
yes, that's right.
Okay.
Might
So
be worth putting them
this is
Yeah,
as total densities. I think it's a
Yeah.
good question.
yeah. And this one, of course, the adiabatic is bad.
well, adiabatic does not
Doesn't
even
even have that. So
have-
oh, it's the same, right? So you wouldn't
Yeah.
even be
yeah,
able to
we
tell the
wouldn't
difference.
get
Yeah.
the
And whereas the dressed is pretty good, no?
yeah, the well, except
Yeah.
for maybe the
Well,
case.
that's-
Well, it's still nice.
Yeah, especially when you looked at the total density.
Yes, exactly.
Yeah.
Yeah.
Well,
Well, actually, if I mean, maybe we should just quickly show that, and I'll pull it up for
mhm.
that other while you finish up here. I'm just going to pull up the example
Okay.
where you do provide
Uh-huh.
excite state for predominantly single excitation character.
Yeah.
I think
You
well,
have that,
I have that in my presentation, I
okay,
guess.
okay, maybe just
the
quickly.
case
So a
with
different system where it was a self-Coulomb helium,
yeah,
right?
exactly.
And then just to
I
see
can-
the difference between cone sham versus versus the TDDFT density, adiabatic SMA density, right?
Mhm.
Do you have it right now? You can,
Yeah.
because that might at least answer one part of the question.
I think
then we should-
is it here? What?
So we know.
Yeah.
You have to set that.
Yeah.
Yeah, I guess it's
Ah.
here, right here. So in the 1D helium, the concham
There you have
right
it.
there by the
Yeah,
green,
that line, no?
and
Wait, the green dash line.
green dashed line.
Yeah.
Yeah, and
Okay.
Oh, okay, good.
yeah.
Okay, so there's
So
a
the-
green dashed, and that is, yeah, it's
yeah, it misses.
kind of there, but not.
Yeah,
Right,
Uh,
it would more correspond to the second state, wouldn't it? L equals
Second,
2, I equals 2 figure, because you're,
Mm.
for the mixture of the single and double, we're in that. I mean, I'm just saying, like, the lowest one has
mhm.
the biggest differences.
Yeah.
because of the exchange.
Yeah, we could show it in the paper, I guess.
Yeah,
But
exactly.
but it's yeah, we also showing the DSP case there, and it's gonna be. Although that's just one
Maybe just
one-
little inset.
one little plot.
What do you think?
Ah. Yeah. For back to the double excitations, we also calculated it with LDA kernel, and well, that's not that different, although well, adiabatic SMA.
So that ALDA, no? I mean, just, and that's, yeah, that's okay for the first one, but not for the third, no, because it doesn't even have that.
Yeah.
I think this is conceptually really super nice that you have this from response. My question is, how do I get that from time propagation? Right? So I can see, I mean, if I take this thing and hit it with a pulse,
Yeah.
the density oscillates, right? And then I just have to basically, I mean, but that's the transition density, right? That's not the excited state density.
Yeah.
So the transition density I could easily get from time propagation. What would I have to do?
You mean by Fourier transforming?
Yeah. Because it's just the transition density multiplied by e to the I omega t, right? But how would I get this from time propagation? So if all I have is my density, a time propagation algorithm, and a source of perturbation, which can be anything I like, how would I get that from time? I thought at some point I had convinced myself that this can be done. And if I'm not mistaken, I even have it as an exercise in my TDDFT book. But I have absolutely no idea. I have absolutely no idea what I was thinking. I thought I had convinced myself there was a way to get it from time propagation. I have to think about it.
Yeah, I have to think about it too, but given that in the adiabatic sense, like if you did it adiabatically, could we then return to the time-independent perturbation theory idea? And
Right.
then measure the energy somehow, but we don't have energies in time propagation. That's the
Yeah, we
problem.
don't
I
have
mean,
energies.
how do we define those exact energies in time
Mhm.
propagation? So maybe not through that. Then the question is, well, okay, if you had a stronger pulse, right, then theoretically, right, then you will, in your, like in quadratic response, then you do
You
probably
have population transfer. You
Yeah.
have actually
something that
you actually populate an excited state.
Yeah, then is there a way to extract that?
Is there a way to extract that?
I should
wanna-
turn this up. Okay.
I want to.
All right.
I'll think about that a little more. This is wonderful. I like this a lot. It's really, really nice. And
Conclusions.
Okay.
I get it. Yeah, the conclusions are great.
Recording.